Welcome to Mastering E. Today we'll be looking at problem 10.1, which asks us to determine the current in an AC circuit. We'll be using input impedance to help us throughout. So first, what we need to do is actually find the input impedance. So the first thing that we're going to do is look at the first component that needs to be converted into impedance. So this would be, of course, the capacitor. So the 1 farad capacitor needs to be converted into impedance so that we can solve the circuit. We can do this by using the formula 1 over J omega and the capacitance. Okay, so calculating this should be pretty easy. It'll just be 1 over J, and our omega will be 10. That means our capacitance is 1 farad. Alright, so this will just be equal to 1 over J10. And next we'll do our 1 Henry inductor. We'll use the formula J times omega times our inductance. And again, this is a pretty easy example, so we'll just be using J 10, 1. Just filling in on all those values there. Now, one thing we want to do is make sure that our impedances both look the same. Now, we don't want one to be fractional and the other one not to be fractional, so we'll just convert this one into the non-fractional form, and that would just be negative J.1. And we can clear this up by just saying J10. So these are the impedances of these two components, the capacitor and the inductor. But of course, we cannot forget our resistors as well. So to find the total impedance of the circuit, we'll need to add the resistors together with the inductor and the capacitor. All I have to do is add all the components as if they were resistors, since they're all converted into impedance. So this means that our impedance formula for the input impedance is equal to 1, which is our first resistor, plus our capacitor, inductor, and other resistor, all in parallel. And of course, we know how to do resistors in parallel. This is pretty simple. So we'll just add all these parallel parts as if they were resistors. So we need 1 over negative J.1 plus 1 over J10 plus 1 over 1 raised to the negative 1. Now for this would be a pain to calculate by hand, so we will just type this into the calculator, and as long as my calculator isn't broken, the answer should be 1.1001, and then minus 0.0, we'll just call this 0.1 J. Now, if you wanted to, you could, of course, convert this into polar, which would be 1.015 with an angle of, I think this would be negative 5.65 degrees. However, my calculator in particular does not like polar very much, so I'm just going to keep my answer like this. So this is the answer for our input impedance. From here, we just need to calculate the current, and this should be relatively simple since we're essentially just using V equals IR just in the AC form. So solving for I, of course, this is V over R, which we can write this in two ways. All right, so this means our current is equal to V over R, which you could write as 2 angle 0 degrees, getting the 2 for the coefficient here, and 0 degrees because there's no degrees appended here. And then this would just be over our 1.015 angle negative 5.65 degrees. And then this would yield 1.9704 with the degrees of 5.653. So you could do it like that, or if your calculator is like mine and it does not like polar, we could also just do it in the other way, which would just be 2 over 1.01001 minus 0.1 J. And we just get 2 because, of course, there is no degrees here, so our voltage is just 2. And plugging this into our calculator yields 1.961 plus 0.194J. All right, so now that we have our equation in polar, we can write the final answer, which is just going to be our current formula. So we write our current as a function of time is going to be equal the leading part of the polar expression, and then the function cosine, and our frequency, which is 10t, plus our angle, which is 5.653 degrees. And this is our final answer and what you should have gotten after completing this problem. If you'd like to continue learning, the full playlist for chapter 10 will be on screen now. Other than that, thanks for watching.